Okay, good afternoon, everyone. Welcome to EECS151 to 51A, Introduction to Digital Design and Integrated Circuit. We're having our 22nd lecture of the semester, almost the end of the semester. And as we discussed earlier, we have finished the first two modules, digital design and microprocessor pipelining, the first module, and second module, the CMOS logic and the CMOS delay. And then we're moving, we're navigating the third module at this point, different combinational unit and also sequential components. We discussed the flip-flop design, started from latches and how we can actually construct flip-flops. And we started some of the discussion on the timing front. In today's lecture, we're going to continue that discussion, wrap up the discussion on the flip-flop side, and then talk about how we can actually build large, dense memory using SRAM and what are the different behaviors associated with SRAM. So before we move on to the SRAM discussion, looking at some of the recent new adventures from the different companies. In some sense, we talk about the different business and the different new new pieces hardware being released, even just actually during this semester, which is pretty surprising given there's like a lot of challenges overall, but the tech industry overall actually doing fairly well. And we have seen a lot of really interesting products actually being released. And they're, especially from AMD, we probably didn't discuss, but if you're following the news, there has been actually really exciting announcement from AMD, both on the CPU front and also on the GPU front. And thinking about some of the new, more recent advances, it's interesting to think about some of the AMD's new move in really thinking about data center business, high performance computing business, and even maybe also in the machine learning business. So one of the more recent announcements, again, there have to be multiple AMD announcements on both CPU and the GPU front. Many of them are very exciting. One of the new recent announcements actually focusing on their data center and also high performance computing business. This is their MI100 GPU card here. This is actually basically a direct competitor for NVIDIA's A100, really thinking about the data center and high performance computing business. Although this card looks actually more targeting to the high performance computing compared to data center or like the machine learning, on the machine learning front, where A100 does have a big advantage there. In some sense, the architecture actually looks similar. If you actually just zoom out again, there are similarities and also differences between the different companies and different processor. But if you just zoom out and look at the core features, especially the feature that they are marketing these days, like a lot of emphasis on HBM, which is very important when you think about the data center business. And in this card, AMD officially announced what they call matrix core. If you recall, like we talked about the tensor core in NVIDIA GPU started from the Volta generation. So it's already, I guess, at least 3 years back when NVIDIA started the Volta generation and added a tensor core there. Although it's called actually tensor core, it's basically doing a matrix multiplication. If you look at the CUDA primitives, is basically called MMA, basically matrix multiply and accumulation there. So this is also, which is at least from the name point, like a very high level, if you think about the AMD's release, where they call, instead of tensor core, which has been taken, they call their new feature matrix core. Likely it's also doing a matrix operation to accelerate, for now, mostly thinking about HPC, but there could be an interesting angle also in the deep learning space, especially if the software front, if there's also a better integration for the software framework, both PyTorch or TensorFlow, there could be also a very interesting story in using AMD's card for future data center and also machine learning front. So a lot of interesting announcement from all the different companies. And this particular one from AMD in thinking about new GPU for data center and HPC, And at the same time, we also recognize a lot of today's processor, because machine learning is so dominant, it's almost like another component that everyone need to consider. And this matrix core, the new addition to the AMD's GPU, definitely reminds you a lot of the Tensor Core that has been part of the NVIDIA GPU ecosystem for 3 generations already. So interesting time, interesting announcement, and also interesting market opportunities. At the same time, it's pretty impressive just to see the range of products actually being announced, especially from AMD in the past few months, ranging from CPU, gaming card, and now high performance and deep learning GPU. So a pretty wide product portfolio from a single company. And then we also talk about the Xilinx acquisition. So the portfolio is definitely fairly diverse, and it's interesting to see how the similarities again between those architectures and how they would actually compete with each other when we actually can measure, when we have more a closer look of their performance in the very near future. Okay, so that's some more recent announcement from AMD in thinking about high performance computing and also deep learning performance. So with that, let's transition to our third module in thinking about sequential element. So we talked about like flip-flop and the latches before as a way to actually store or track states. And a very important part is also a different delay component. You notice the delay discussion, we started from the combinational logic in the second module where we discussed the CMOS logic and how you can actually turn CMOS logic both for the gates part and also for the wire part, basically turn them into an RC network to actually calculate the delays there. And the one thing we'll notice that similar discussion also exists when we talk about sequential logic. And there's also different delay component that's actually very, very important when we think about how we can actually make sure we time our circuit correctly so that it satisfies all the different delay constraints here. Most of our timing discussion is focusing on the flip-flops, and we discuss flip-flops can basically be built with a pair of latches. And our timing is also mostly focusing on the flip-flop because that's basically the most commonly used design using the edge-triggered transition. They're also, especially generations back, the latch-based timing was also very popular, especially for high-performance computing, but getting less popular these days just for stability and also better resilience reasons. So we will be mostly focused on the flip-flop timing discussion and thinking about how we actually change that. But if you're interested, like more advanced digital design class, like 251B or 241B, will cover more detailed latch timing and how we can actually analyze latch timing there. So with that, in today's discussion, we'll do a quick recap of the timing analysis for flip-flops, and also some of the non-ideality exist in the flip-flop timing analysis and how we can actually at least account for those non-ideality when we think about the delay behavior and also the frequency of our circuit. And then we'll move to our SRAM discussion. We'll start with a brief overview, thinking about how we can actually build two-dimensional array structure, and then get to one of the most commonly used design, the 66 transistor SRAM cell. You may notice we talk about the two very important basic components. Whenever we actually get to any storage element, you will see actually a lot of similarities when we get to the SRAM cell. And the part of the discussion there is that there are different transistors there, and making sure that our SRAM can be both read, accessed correctly, but also can be written correctly. We also need to size the different transistors actually appropriately to make sure it actually performs the right function. So we'll also talk about some of the sizing constraints in the SRAM part. We'll not have time today in thinking about actually memory decoder, which is also very important to actually generate addresses to access the memory cell. So we'll leave that discussion next week when we talk about both the memory decoder and also thinking about how we can actually leveraging SRAM to build caches, which is one of the most important building block, especially in modern processor, in modern computer processors. So we'll do the cache discussion next week after the guest lecture. So with that, just a quick recap. We talk about flip-flop timing characterization, and we talk about there's three important timing whenever we need to consider whenever we start thinking about flip-flop. It's basically related to the relationship between the input and the clock, and also a relationship between the output and the clock, those two pairs there. And specifically, we talk about between the input and the clock, the first timing constraint is what we call hold time. It's basically the amount of time where after our clock edge, the data input still need to be stable so that our output can be fully charged or discharged to get the right output. So that's hold time, which happens after the clock edge. There's also another constraint, again, between the input and clock is a setup constraint, which is happening actually before the rising edge of the clock. This is to make sure that our input is actually stable before the rising edge of the clock so that the data can actually be properly latched in the rising edge transition. So that's a setup and hold time pair. One is happening before, which is a setup. We need to set up the signal before the clock transition. We also need to hold the signal after the clock transition to make sure that the data can be properly propagated through. And there's another timing constraint is what we call clock to queue delay. So that's become the other pair is between the output and the clock. This is to measure the delay from our clock edge to data output when the new output is actually stable. It's basically the propagation latency between the clock to the output. So those are the three important delay consideration. And why they are important? Because they actually affect the frequency of our hardware, of our circuit, and also our processor. We need to actually set the frequency. We talk about how frequency has been scaling or stopped scaling in the past decade. So very important design metric is to set the frequency of our hardware, and all the different factors actually affect the timing behavior of our processor. So we discussed this last time. We'll just do another quick recap before we talk about the non-ideality of the clock. So if we think about the delay, so before we have been mostly focusing on the combinational delay, right? The delay inside the combinational logic. Now in this part, we start introducing, we also need to think about the sequential part. We have the flip-flop here, both before this, at the beginning of this stage and also at the end of the stage, right? So both delays actually involved with the flip-flop are also need to be considered when we think about how we can actually set the frequency of our circuit or our processor here. So we have talked about our frequency or our delay or our clock period need to be actually greater than basically the critical path of our hardware, right? So you need to make sure that all the signals can actually propagate through. And in that discussion, we have our clock period here. All the signal need to be propagated through correctly, not only just for the combinational logic, that also includes what we discussed earlier, the flip-flop before our combinational logic and also the flip-flop after our combinational logic. So in this particular case, if we think about the critical time here, or the longest path actually exists, when we think about the propagation delay here, we first, as a rising edge clock, at the beginning of a new clock cycle, we first need to go through this clock to queue delay to actually make sure our queue, our output, is actually correctly being properly set by the input. So that's the first part, the clock to queue delay, as we specified here. And once queue is actually set correctly, that's basically the delay to actually go through the combinational logic. We did a quick exercise last time. So when you think about combinational delay, one thing very important is also to recognize what are the false paths exist in your combinational circuit, not only just like doing the max of all the possible paths. Sometimes the paths actually are conflicting with each other. So you also need to analyze your circuit carefully there. So after going through the combinational logic, we get to our second flip-flop here. So here is what we need to make sure that we also have enough time to actually satisfy the setup time constraint so that our between the input data and our clock, so that we can actually properly latch our input data. So if you think about the clock period for this circuit or for this processor, not only just for the combinational logic, we also need to consider for the first flip-flop, we also need to consider the clock to Q delay. And for the end flip-flop here, we also need to consider the setup delay between our input to clock. So this is actually what we need to consider when we think about our clock period, which will determine our clock frequency. So that's the first part when we think about the timing constraint. Another part, we also talk about the hold time violation. Here, we also need to make sure our data need to be held long enough actually before, so that to make sure our data can be actually latched correctly in our flip-flop. So with the hold time constraints, basically saying the data shouldn't be actually changing very quickly because it needs to actually be stable for a while, even after the rising edge of the clock, so that our data can be properly propagated from the input of our flip-flop to the output of our flip-flop. And if you think about after a rising edge, what really happened in this part of the circuit. So after a rising edge of clock, we get a new output from the first flip-flop, R1 here. So there's a clock to Q delay. And if the signal is actually propagated very quickly. So now we're looking at the race condition where whether we would actually overwrite this data, the input data to the second flip-flop, so that it actually violates the hold time violation here, the hold time constraint here. So the scenario would be after the clock to Q delay, if my combinational circuit, especially my minimum pass, is actually very fast. Let's say we actually don't have any logic, or maybe just have a couple inverters there. So it's actually so fast. In that case, actually I get my D, the input to my second flip-flop, being updated so quickly that we actually lost the original value that's in, which was the input to our second flip-flop here. So in that case, it actually violates the hold time constraint here, that we don't have a stable signal after the rising edge of clock to make sure the signal can be actually propagated correctly to the output of our flip-flop. So another hold time constraint here is basically saying the data propagation after the rising edge of clock, including the clock to Q delay and the combinational delay, need to be long enough so that my data is not, my input data to my second flip-flop is not overwritten, so that we can actually satisfy my hold time constraint. So the previous data is actually propagated correctly before this data is actually being overwritten. So that's basically the hold time constraint here. So one thing you notice here, this is actually purely internal to your circuit, right? So this is basically what's your clock to Q delay and what's the complexity of your combinational logic. So if you think about the setup time constraint here, that our frequency, our clock period need to be longer to actually consider the setup time constraint here, right? So if we run into a setup time violation, we can always just slow down your clock. That's always one easy thing to do to actually make sure that your hardware, your circuit is still functional. But hold time violation is actually a lot more critical in the sense that a lot of times there's not a lot of things that you can do unless you can actually change your circuit, because everything is actually baked into your circuit assumption here. This is really about how much logic you really have in your circuit to make sure that it can actually propagate long enough without overwrite the previous data here. So the hold time violation is a lot more critical, and there's not a lot of like simple workaround that you can do, like just changing your clock frequency. You really need to think about what's actually inside your combinational logic and make sure there's like no short paths exist in your circuit, which can actually potential trigger this risk condition and the triggers hold time violation here. So that's just a quick recap in thinking about both how setup time and hold time will actually affect the functionality of your hardware. So that's not only just the critical path delay, which can be a little bit can be straightforward when we think about what we talk about, different logic gates delay and what's actually being involved there. But now we actually have a lot more components here. We also need to make sure we have enough buffer so that the signal can also be propagated correctly through our flip-flop stages here. So if we look at just a quick recap, if we think about the different events really happening at each individual clock cycle here. So this is basically clock cycle between two rising edge of clock. So within this clock cycle, if we think about what we discussed earlier, the hold time is what things happen between the input and the clock. And our clock, and it specifies the behavior of how long the input need to be stable after the clock, after the rising edge, after the clock transition, right? So we need to make sure the data is actually stable for the hold time violation, for the hold time constraint before this data is actually being overwritten. And we also talk about setup time. And again, setup time is still the input and clock pair, but this is describing timing constraint that actually happened before the rising edge of clock, how long actually our signal need to be stable to make sure the signal can also be propagated propagated correctly from the input and output. So those are basically relationship or different where setup time and hold time are actually specifying the timing behavior. Again, one is after the clock cycle, after the clock edge, another is before the clock edge. With that, between the setup time and hold time, that's basically where we can actually insert our logic, right? So that's what we have been discussing before, like all the different combinational logic, which have different delay, different timing behavior, that all of those switching are happening actually in this period to make sure that our system actually function correctly. And a lot of time you may already notice in your synthesis report when you look at your design, a lot of time you actually observe like your design is typically actually shorter. It doesn't actually take the entire clock and entire clock period. And typically you also notice it will also report the slack that exists in your design, right? So if you have slack, it's basically you have some actual buffer to actually to handle some other conditions. We'll see later some of the non-ideality will also trigger in that will also eat some of the slack time that you have. But if you also want to optimize your design, you can also add more logic into your design to actually have have smaller slacks to actually make sure you maybe have smaller number of stages to make sure you actually use all the available time that you have here. So this is basically a very typical delay behavior or timing behavior that you will actually see in a lot of circuit analysis. So we always need to have enough buffer for both our setup time and hold time. And then between those, we can have actually our time for our transitions. And typically there's also some slack we need to actually provision to make sure our circuit can also behave correctly. So one thing that's also related to the timing behavior, we haven't talked too much before, is that we always assume our clock are actually synchronized with each other, right? We talk about there the multiple registers, right? All of them have a clock input. We always assume that all of those actually get the same clock. They always transition at the same time. We discussed briefly during the SOC Insight guest lecture, where speaker talk about the clock distribution network and some of the concerns that they have in actually optimizing the clock distribution, especially for large SOC. So one thing when you really need to consider is that when you have a large, like a piece of hardware where you need to actually send your clock to all the registers, right? You have plenty of registers in your design and all of them actually have different, like is being placed at different places and also need to be routed differently. So all of them could actually potentially have a different delay. And that's already one component when we think about the non-ideality that actually triggered when we have different delay. But there could be also other noises. Like we also talk about the noise in our circuit, and that could also trigger the different delay profiles when we think about how clock is actually distributed to the system. So if we think about the clock, how the clock actually distributed, it starts from the clock generation, and then we have actually our clock tree distribution network to actually propagate the clock signal before it actually arrived at our sequential logic, our flip-flop here. Even during this part, right, we talk about the devices and we talk about fabrication process earlier, which is a fairly complex process, right? It's really hard to actually make all your devices actually the same. They all actually behave the same and they all size the same. There are always non-perfect sizing or non-perfect printing when we think about how actually silicon is actually being fabricated. So those are always have some like variation when we think about the different nodes or different gates as part of the clock distribution network, which could also trigger, like we'll talk about how the different gates can be basically viewed as RC network with different resistance and the capacitance. They will also contribute to the delay actually differently. And then we also talk about interconnect. I talk about the wire delay, which is also very important factor. And whenever we talk about interconnect, we also talk about the different, like all the flip-flops can actually be placed at the different places. And whenever we start propagating signals to all the different of them, it's actually really hard to actually make sure you have the same delay. That's actually a very tricky problem there, because they all have different wires and they all physically actually placed at different places. And all of those actually could actually also lead to a variation in the clock signal in when when each register actually receive your clock signal. So that's the interconnect part. And also we talk about noise. So power supply, you could also have like noises in your power supply instead of just, we always say it's VDD, but there could be also different or slightly variation in terms of our power distribution network. If the power actually also varies, that also affect the latency, right? So we talk about the voltage and how that actually affect the propagation delay, the latency actually when we actually propagate signal through the RC network. And finally, like there's also different load. If we think about all the different consideration we need to actually consider, just it's really hard to say like everything is perfect when we think about the clock distribution. Like even we get to the eventually different hardware, we're also different registers. The clock will actually be driving different load with different capacitance, and again, all of those will actually lead to different delay. So there is also coupling effect, which will be another capacitors in your distribution network, and also the temperature effect that will also change the delay. So there's like a lot of other factors actually will affect how clock is actually arrived, both in terms of space, like relatively compared to each other, and also just for each flip-flops, how actually different clock edge actually can be actually different from each other. So this is fairly high level. We're not asking you to actually analyze this or to actually quantify this, but at the same time, we should actually at least be aware, like when you think about clock, it's easy to think about it's a very clean, beautiful signal. It just like, oh, always rise perfectly, like the way we do simulation. But there is actually a lot of practical concerns when we think about how clock is actually propagated to different flip-flops in our design. So with that, like we talk about how those factors, what are those contributing factors, but eventually all those contributing factors will basically affect the way we see clock, especially when we see clocks across different flip-flops, across different registers with like two key factors. We'll briefly talk about the pulses, but typically it's mostly the two key factors. Those are basically related to what we discussed earlier, how the arrival time of our clock can be different in space and time. So one is actually thinking about the space differences, and another one is actually thinking about time differences here. So what do I mean by that? So space differences is basically trying to say, okay, so if you think about all the different registers or all the different flip-flops actually in our system, all of them have actually a clock signal. Right? The spatial differences is basically trying to quantify the differences in terms of between different flip-flops, when we actually compare their clock signal, whether they actually arrive at exactly the same time or there's actually small delta when we think about the clock arrival time. So the skew is basically say the differences. Like in this example, you have two flip-flops, each driven by their own clock signal here. It's entirely possible that the clock signal for the first flip-flop is actually arrived earlier compared to the clock signal for the second flip-flop. In both cases, the solid line here, where the arrival time for the clock signal for the second flip-flop is actually arrived later. We both call them clock signal, but they can actually not actually show up the same time. So the spatial differences, or what we call clock skew, is basically a way to actually specify what are the differences between two clock signals that are actually used to trigger two different flip-flops that located in two different places. So are they actually the same? In which case they are actually, there's no skew, the skew is 0, or there's different, where one flip-flop is actually, the clock signal of one flip-flop is actually arrived later than the clock signal of the first flip-flop as shown here. So the skew, clock skew is basically talking about the differences between two clock signals. Each is used to trigger their own flip-flop, but there could be differences because of all the reasons that we discussed earlier, the differences in devices, differences in loads, and also differences in the wires where they could be physically located in different places, and all of them trigger the differences when we think about the clock skew. So that's what clock skew is trying to measure. When you hear people talking about clock skew, they're basically talking about two clock signal, each of which is used to power or trigger one of the flip-flops, but whether those two clock signals are actually synchronized with each other. So another part is what people call clock jitter. It's also related to the non-ideality that we discussed earlier, but instead of between two clock signals, so this one is actually more thinking about within each clock signal, whether it's actually always deterministic in the sense that it happens is always has a rising edge at a certain point and I'll have a falling edge in a different point, whether it's actually always deterministic or there is some what they call jitter, like some shifting actually going on so that every time, every rising up edge of a clock, you may actually get a different, slightly different clock signal. So this is really measured between the rising edge of a clock for the same clock signal. So this is what they call like more temporal. So this is for a specific clock signal, whether we always actually have the same behavior or there is also some shifting going on so that our clock is actually not that deterministic, that there is always some random noise that actually modulate my clock signal so that my next rising edge could sometime happen earlier, could sometime also happen later, right? So this is what they call temporal clock like variation. This is for a specific clock signal, whether there's actually any jittering going on. So those are like two important, very important factor when we think about clock non-ideality and how it actually change the way we actually think about clock, like timing our circuit and what are the different timing constraints and what we actually need to think about when we actually optimize our design. Another part is the pause width, which is actually more important when we talk about latch-based timing. Again, most of our discussion is actually flip-flop-based timing. We're both basically talking about the edge-triggered behavior, but for latch-based timing, which is actually level transparent, we discussed last time. So it's actually our transparent low or transparent high. So the pause width is actually more relevant for latch-based timing. We'll not discuss that too much for this class because both is actually less relevant these days, especially for like today's high performance processor design. For some of the really high performance design, like latch-based timing is still used, but it's just a very small market at this point. So we'll be mostly focusing on the flip-flop based design and very importantly, skew and jitter are very important, and it will also affect the timing analysis. So we'll see an example focusing on see how clock skew actually change the way we think about clock and how it actually affects the setup and the hold time constraint. And for jitter, you can also convert the jitter constraint into the clock, into the skew constraint in the basically, like you will have like multiple clock. What the worst case would be the first clock actually, when we think about the overall critical path, will be the first clock actually have jitter that's showing up later, while the second clock actually have jitter that's showing up earlier. So those are also related when we think about the differences between two clock signals, between two registers, because those are what we're interested, how signal is actually propagated through a clock stage here. So let's take an example here. So this is what we have seen before, right? So this is the timing constraint that we have for our circuit for the clock period, right? So it needs to be actually longer than the clock to Q delay, and then going through the combinational logic, and then need to satisfy the setup time constraint. Again, between input and the clock, before the rising edge clock, it needs to actually satisfy the setup constraint. So that's what we discussed earlier, right? So now what if, whenever you see actually two different registers here, you always need to ask, oh, whether those clock signal actually are showing up at the same time or at actually a different time. Basically, whether there is clock skew actually exists between this pair of flip-flop in our circuit here. Let's say there is actually a clock skew exists so that let's say in this case, the arrival time of my second flip-flop, the rising edge of my second clock is actually being delayed. So there is a small skew actually showing up so that my second flip-flop, just in this hypothetical example, let's say just have a longer wire. So that's actually the arrival time of my clock is actually have a small skew here. So how would that actually change like the delay analysis that we discussed earlier? So in this time, we think about the overall latency here. We still have our clock to Q delay. We still have our combinational delay. We talk about our setup time. The setup time is actually between this input and the clock of the second clock, in this case, clock 2 here, right? So the setup time is actually between this dashed line to this dashed clock, because this is a clock that we really need to monitor for the second flip-flop here. So we basically, with that, we have a longer setup time with this. So in this case, when we think about the entire clock period that we actually want to provision for this circuit, so we have this clock period here, and because my second clock is actually arriving later, so in some sense, it's basically between my first clock and second clock, I actually have a slightly longer time, just naturally, not because of my combinational delay is faster, not because actually I have a faster clock to Q delay, not because of that. Now I have a bigger buffer, I have a slightly longer time, just because my second clock is actually arrived later. So I have actually a longer time to process the entire information here. So if the second time, in this particular case, if my actually clock skew is actually, if my second clock with the clock skew is actually arrives later, so I actually have slightly more time to actually propagate this signal. So in this case, it actually helped us. So if we think about the timing analysis, we could still have our clock, but now when we think about the entire delay, we basically only need to make sure my clock and my skew here, in this case, we have basically my second clock is actually later, so we have a positive skew here, need to be actually greater than the clock to Q delay, the logic propagation, and also the setup. So that's something we basically need to consider, whether where the skew is, right? Whether it's actually helping us or actually hurting us. In the other example, what if the arrival of my next clock is actually showing up earlier? So if it's actually showing up earlier, so this time the skew is actually hurting us. So we actually need to make sure my clock actually, so we basically have a negative skew here, we actually need to make sure we actually budget our clock correctly so that if my clock, second clock is actually arriving earlier, I can still accommodate all the latency, like the clock to queue delay, the logic delay, and also the setup delay for my entire path. So this is basically how thinking about clock and between the two spatial relationship of my first clock and second clock, sometimes it actually help with our timing analysis, but sometimes it also hurt, right? With our timing analysis. So that's actually really matters whether it's actually a positive skew or it is a negative skew. So this is the setup time analysis. And we also talk about our hold time constraint here. The hold time is basically we need to make sure the signal is actually not overwritten, right? So if my signal is actually propagating too fast, it shouldn't actually overwrite the signal that we already have in our input. So in this case, if we think about the hold time constraint like scenario, here we have two clock signal. This is my second clock and this is my first clock. So if my actually second clock is also arriving later, so I'm actually arriving late, instead of arrive at the same time, I'm actually arriving later here. So in this case, when we think about our propagation delay, which is a clock to queue delay and also a logic delay here, need to actually satisfy where we still have our hold time constraint. So this part is the same. It's being pushed because my clock actually arrived slightly late in this case, right? Because I have a small skew here. So my hold time is actually being pushed later. So I have a small skew here. With that, I need to actually make sure my clock to queue and also my logic is actually long enough so that it can compensate not only like what we talked earlier, the hold time constraint, right? You need to actually hold the signal, make sure the signal was held long enough before being overwritten. Not only the hold time constraint, but also the skew factor here, because I only start counting my hold time after my clock has actually arrived, right? If my clock has not arrived, we also need to compensate that gap before we start actually compensating the hold time. So with that, if there's a clock skew actually on the receiving end, on the second flip-flop, it actually need to make sure the signal, you have long enough latency to actually not only compensate the hold time constraint, but also compensate this skew here so that it's actually long enough to hide this latency. So this is pretty high level. Again, this is really understand all the different and it's the different contributing factors of your signal. And really importantly, that we typically think about an ideal world where we basically get all the ideal signal directly, but in a real world, like signal don't all show up the same time. It never happens, right? So you really need to think about the worst case scenario and how you're, when you think about the different component of your circuit, you really need to compensate not only just the normal case, the ideal case, but also the non-ideal case where clock skew actually play a fairly important role when we think about design, especially when you get to actually really large scale. Like for small scale, like in this, we're basically using a fairly artificial example, right? Here, they're actually pretty close. But in the really big scale, when we actually talk about clock distribution network with actually all the different wiring and also different buffering being inserted, sometimes it can actually make a significant difference. And with that, it's really important to, at least in your mind, when you think about delay, it's not only just the signal delay, but also consider the non-ideality of your clock when you think about how the different contributing factors actually put together when we do the timing analysis. So that's basically wrap up our clock discussion. Any question so far? Again, very important, we started with timing, not assuming the clock non-ideality, that just really making sure it's not only the combinational part, but also the sequential part, the register also contribute to the delay. And then later it's really not only the delay part, the clock signal may also be non-ideal, which could also lead to different, you also need to budget your circuit to make sure it actually meets those constraints there. So with that, on the logistics side, so midterm 2 is done. Good job, everyone. All of you, most of you actually did really well. So during the discussion today, we'll release the grades and we'll also go through some of the common mistakes in our midterm 2. I already went through your exam. I think all of you, most of you actually did significantly better than midterm 1. So really good job, everyone. And this is, I would say, the second module is actually one of the most challenging module. If you think about the entire, the 3 components of our class. Like this is the second module is challenging, both for undergrads who don't have a lot of like EE experience before, and also for some of the grad students. This part may also not covered actually in the way we typically teach digital logic. So all of you, most of you did really well and also improved significantly from midterm 1. Really good job. And I would say this module 2 is actually very different and very challenging. So it's good to get that done. The current module is actually a lot easier. You may notice now after you feel comfortable in analyzing each individual transistors, now we're basically assemble the transistor differently, but following the same principle. You'll see more, we'll talk about that, how that actually affects the flip-flop design, and you will also see that when you actually get to the SRAM part. So the third module is easier. So it's good too that we get the second module done, and good job, everyone. Most of you actually did significantly better. And if you didn't do too well for midterm 2, it's okay. Feel free to reach out either to me or to other teaching staff so that we know how we can help you. The midterm can be collaborated. So in the final, there will be 3 sections. The first part is basically covering the first module. And if you do well in the first part, that covering the basically the midterm 1 part, we can use that to collaborate your midterm 1 score. And similarly, in the final, there will be also some problem basically covering the second module. And if you do that part well, you could also use that to collaborate your midterm 2. You still need to finish the entire final for all the questions in the final, but it will be easier as it will be more like review for you to use what you already reviewed in midterm 1, midterm 2. So it will be easier, and there will be opportunities that you can actually use final to collaborate. So for some of you who didn't do too well or not as well as you expect, that's okay. There are still opportunities. And at this point, I really don't think it's worth actually dropping the class or anything. You have already put a lot of effort into this class. Feel free to reach out to us and see what we can help. And there's definitely like Copper can help with that. And the project is still ongoing, which is a very significant part of the lab grade, right? So just stick to it. You can do it, especially at this point. Don't feel discouraged. And if you have any questions or challenges, feel free to let us know. But overall, good job, everyone. And you will see in today's discussion, today and tomorrow's discussion, we'll go over the midterm 2 problem here. And really important for this week is project checkpoint 2 for both ASIC and FPGA lab. I know this is a fairly substantial checkpoint, really important. Make sure you do things on time. You look at the project timeline, it's actually pretty packed, right? So we structure this so that you have enough time to get at least the majority of your design done before the Thanksgiving break. So definitely do that. We also budget enough time for our GSIs to talk to all the students, including both the lab time and also office hours. Especially for FPGA, for folks in the FPGA lab, use a spreadsheet to reserve your slot this week. It can be both for lab checkoff if you have the second checkpoint. If you have finished that, reserve your slot to actually get the checkoff. If you think you need more help, also reserve a slot so that we can see whether the GSI can help you. We definitely budget enough time so that we can talk to all the group during the labs and also office hours. So reserve your time early and use that to reach out to your GSI to both get your checkoff done or just let them know where you are so that they can help you. So make sure you talk to your GSIs this week, and hopefully we can wrap up checkpoint 2 before the break, and then we can move on to checkpoint 3 moving forward. We do have a guest lecture coming up this Thursday in 2 days, so Thursday this week. So this will be actually focusing on the design verification part. Many of you mentioned that in your interview, you were asked about verification questions. So we are very aware of this. We have been thinking about how to actually get verification covered through actually a formal course. We do have a grad level courses focusing on formal verification. A lot of grad students actually really like it. So if you're interested, also take a look at there, but we do want that to actually get covered. So we have a guest lecture. Today I posted the details about the guest lecture on the Piazza already. So it's really fairly informative. We already have Srida actually spoke with us last year. It's a fairly informative guest lecture. So, and we want to actually bring that in also for this semester to get you that perspective in not only thinking about the design, which is the focus of this class, but also thinking about some of the practical verification challenges in industry design side. So you may notice the lectures, both the lectures and the homework is getting a little bit lighter because we do want you to focus on the project. Very important, get your project done and as much as you can before the Thanksgiving, and after that, get the entire project done before the final week. So we only have one more homework left. So it will be out this week, and it will be a 2-week homework again, so that you have enough time to actually work on that, and that will be the last homework for the entire semester. So we're wrapping up, and I think all of you actually did really well, especially in midterm 2. And let's get the project done, get the checkpoint done first, and then get the project done before we actually march to the final. Any questions? Comments? Okay, great. So now we talk quite a lot about flip-flops, and now it's time to actually transition to SRAM, which is another very commonly used storage element, especially when we're thinking about like memory design in both the way we think about the caches. We'll talk more about caches next week, but also in some of the more specialized ASIC logic, we'll also see scratchpad, basically SRAM actually being used fairly commonly to cache and stage data locally. So we'll talk about how we can actually use SRAM to actually store instead of flip-flop, which is focusing on like a small number of bits actually being stored, how we can actually use SRAM, especially dense SRAM, to actually store a larger amount of data. So SRAM stands for Static Random Access Memory Architecture. So before we get to the SRAM cell and how we actually built SRAM design, just a very high level, when we actually think about memory, conceptually, we basically always think it's actually a linear array of addresses, right? So we always have a memory map, it's always linear. We start from like the beginning of an address and then keep incrementing. And in this case, every box here holds a piece of data here. So it's just a very like skinny tall style of matrix, so that we actually have a very linear view of both addresses and data. So this is actually fairly impractical when we actually start building hardware to actually store the data. Instead of having a very linear view of your both addresses and data, when you actually think about how things actually being stored, it's actually more like a 2-dimensional array. where you actually need to have actually different row addresses to figure out which row you're accessing, and also different column addresses actually to figure out which column you're accessing. And the ones you actually specify, break down your address into the row address and the column address, you can actually specify a particular cell of the entire 2D array, and that corresponds to the specific piece of data that's stored with this address. So instead of this kind of very linear view, actually, when we talk about memory, we'll see more when we talk about memory decoder, it's actually really two-dimensional. You need to specify the row address and the column address to figure out which cell we are actually accessing to access the data. So if we look at a basic memory array, we mentioned it's actually more like two-dimensional, right? We need to actually have row addresses and also column addresses so that we can actually specify which cell that we are accessing. Some terminology that you will actually run into when you think about any basically two-dimensional array design, especially when we talk to SRAM, is basically the row addresses eventually will become one-hot encoded. It's basically specify which row that we're accessing. And here, this row or the highlighted cell, we'll see how it's actually connected in a minute. This is basically called word lines. It specifies which row, which word we are accessing here. And correspondingly, we'll get to actually column, like we need a cross to actually figure out which cell that we're accessing, right? So this vertical line here is basically specifying which column we're accessing. This is basically called bit line here. So bit line, word line is specifying which row we're accessing, and bit line, we'll see how we can actually use bit line to actually read and write this particular SRAM cell to access the column here. So whenever you see a SRAM cell, is always, you will see actually at least two. So in reality, it's actually 3 lines. You have actually a pair of bit line. We'll talk about that later, but you will always have the word lines for the row address and also a bit line for the column address so that you can access a particular cell in your two-dimensional array. So we also talk about there need to be a decoder so that we can actually get a one-hot encoded addresses and to access both horizontally for the rows and also vertically for the column. We'll not get too much about decoder in today's lecture, but we'll actually come back tomorrow, next week. We actually think about how we actually build row decoders, row and column decoders, especially what are the latency constraints in thinking about the design complexity here. So there basically you have some peripheral logic to actually specify which row and column that we are accessing. And then by setting the word lines and bit lines correctly, we can actually access each individual SRAM cell, and the data is actually stored in the cell. So in today's lecture, we'll be mostly focusing on the cell design, what's really actually inside this cell so that we can store data, not only storing data, but also accessible so that we can read the data out, like doing a memory read operation, and also update this data, like write to this memory so that we can update the value in this cell. So we'll start with the cell structure, how we actually build this internal storage element in our SRAM. So what does a SRAM cell look like? This actually looks fairly similar to our latches, right? Remember when we talk about, before we get to the latches, whenever we talk about storage element, we always talk about there is some kind of cross-coupling inverters so that we can actually stably store a value, and also using this feedback, using the feedback loop, using the regenerative property in our CMOS logic so that we can stably store either 0 or 1 in our circuit. So whenever we look at the storage element, this is very familiar. This is basically the same as what we have seen in latches, using this feedback loop or cross-coupled inverters to actually store our element. So whenever we talk about stored value, this is also the same as what we already saw in latches. We actually always store a pair, both original value, if the D is 0, the inverted value, the bar is basically 1. So we basically always store both 0 and 1 is actually being stored here. And with this positive feedback, we can basically have a very strong, both a strong 0 and also a strong 1 in our system. So this is basically the core cell structure of our SRAM. So you may wondering earlier I said very commonly used a 60 SRAM style structure, right? But now you're only showing us like 2 inverters, right? Each inverter is like 2 transistors, right? We spent a lot of time talking about inverters like a month ago, right? So now there's only 4 transistors. What does the other 2 transistors do? That's a really good question. So far, we only talk about storage, right? So this is need to be actually stored here, but we also talk about it also need to be accessible. We need to actually perform both read operation and also a write operation there, right? So that's basically what the other 2 transistors are used to actually access the value that's actually being stored in this inverter pair. So if we look at how we can actually access this value here, so those are the 4 transistors we already talked about earlier, this inverter pair, so that we can actually store the data here. So now we actually need to have another access transistor, this transistor here, so that we can actually access the value that's stored here. So in this case, this is a 5T SRAM cell. We'll talk about where is the other T coming from later. But in this cell, what happened is basically if we actually want to do, let's say want to actually write to this SRAM cell, we actually want to update this value. We basically set the enable high. So this is an NMOS transistor, right? So we set the enable high so that the NMOS is actually on. So we can actually write our data from D to actually to this inverter pair so that we can actually update this data here. Right, so what we do, like we talk about, there is actually sizing constraints so that we can write the data successfully. We'll talk about that later. We don't get into that for now. But what's going on here is basically we want to write the data from from the input D to the internal of our SRAM cell so that the data can be updated. So looking at this, you may wonder, this actually looks very similar to what we saw with NMOS when we first discussed NMOS and PMOS there earlier, right? And when we first discussed NMOS and PMOS, we mentioned NMOS is really good at passing 0, while PMOS is actually really good at passing 1, right? So that's why we actually always put NMOS as a bottom pull down network so that we can pull down to 0, and then PMOS as on the top so that we can pull up as part of the pull up network so that we can pull up to 1. But if we actually want to use NMOS to actually transfer a 1, it typically gets what we call a weaker 1 here. That's because instead of actually writing directly to VDD, here we use NMOS as a pass transistor. We actually need to guarantee the threshold voltage between gate and source. So instead of writing a 1, we actually write VDD minus a threshold voltage. So this is actually a weaker 1. So it's actually really good as writing a 0, so we can just fully discharge. We can actually get a very strong 0, but not very good at actually writing a 1 here because of basically the same property, the same constraint. We have the NMOS is really good as a pull down network, but not very good as actually transfer a 1 or deliver a 1 because we always need to guarantee this VDD minus VTH gap here. So what should we do? So this part is actually pretty good at writing a 0, right? So if we actually want to write 0, this is fine. But if we actually want to write a 1 here, that's where the challenge, right? If we have 1, we can only write a weaker 1 instead of a strong 1 that we discussed earlier. So if you think about this, we like things to be symmetric, right? So if we actually want to write a 0 here, we are basically storing a 1 on this node, right? So since we are actually pretty good at writing 0, right? What if we actually write a 0 here? And in that case, this node becomes a 1. And after an inverter, it will be actually a strong 1. So we can actually still write a strong 0 here and then get a strong 1, which is the same as what we wanted to do, right? Get a 1 to this node. So instead of access this node directly, we have a symmetrical point here where we can actually just access or write an inverted value. Instead of writing 1, we can write a 0, where we can still use the same NMOS here to actually get a very good 0 here. And that's also being symmetric. And then we can actually, don't need to actually worry about 1. We just, whenever we need to write 1 in this node, we just write 0. And this is always good as writing 0 here. So that's basically why we add another transistor here. It's also an access transistor. This access transistor is basically used to write 1, but it took a detour here. Instead of writing 1 directly to this node, let's say if this is Q, this is Q bar. Instead of writing directly to Q, it actually writes Q bar here. And by only writes a 0, it can still make, basically makes this SRAM to actually store a 1 here. So having this very symmetric cell or symmetric view of our SRAM, this is basically what we have as a 6T SRAM. We have 2 access transistors and 4 transistors to form this inverter chain. So it's actually fairly straightforward. It's actually not a lot of new things added. This is what we had already with our cross-coupled inverters. And now by adding 2 access transistors and MOS transistors, now we basically have our 6T SRAM cell now. So this is actually one of the most commonly used SRAM cell design. Here, there's still a lot of SRAM research going on. We'll see some of them. We'll actually at least briefly discuss some of them. But in most today's, especially high density SRAM design, this is basically a very commonly used 6T SRAM, has very symmetrical view and use 2 access transistors and also 4 transistors to form this inverter loop. So this is a very high, like I guess a high level diagram. We actually break down, you will actually write everything and draw everything in transistors instead of just writing this as an inverter. So this is basically our 6T SRAM. So again, it's a lot easier. It's basically everything is what we have covered in our second module. This is just another way of organize our inverters, our transistors, so that it can perform the specific functionality here. In this case, storing values here in our SRAM cell and having 2 access transistors so that we can both read and also write to this SRAM cell here. So we talk about the word line. We saw the word line earlier. So word line is basically connected to the access transistor, right? Specify, we actually pull up and put the word line high for this specific row. It means that we actually want to access this row of SRAM cells. So both of the access transistors M5 and M6 are on. So word line is actually used to specify whether the access transistors are on or off. Then bit lines. So we have actually a pair of bit lines, both bit line and bit line bar here. Those are actually used to perform the read and write operation. We'll go through them step by step to see how we actually do a read and a write using the 6T SRAM. But here, because we all like specifically for the write operation we discussed earlier, we want to write both 0 here to the Q point directly, or you want to write a 1 here. Instead of writing here a 1, we basically write Q bar as a 0, where we can still write a good 0, and then go through this inverter, and then Q will basically be a 0. So this is our one inverter. This is another inverter. They form a loop here, and then 2 access transistors so that we can actually access the values that are being stored in this pair of inverters and also overwrite the value if we actually perform a write operation. So those are the SRAM, the different cell transistors in our SRAM cell. Let's see how we can actually perform read and write using, again, those 4 transistors that form an inverter, and also those 2 access transistors that actually where what's being visible externally, so that we can modulate the states inside either for Q or Q bar here. C. Okay, so for the write, we already talked about the write earlier. So again, the word line is actually used to specify whether we actually want to access this cell. So when the word line is high here, my access transistor is turned on here. Let's say originally this Q, so we call this value is Q. So we're actually storing a 1 here in Q, and so the Q bar is basically we're storing a 0 here. So when we actually do a write here, we basically write the value that we want to write in our bit line here. So we basically, in this case, let's say we want to actually write a 0. So we, instead of having a 1, we actually want to overwrite what's the value actually already inside our SRAM with a 0 here. So in this case, what we do is basically pull up our word line so that we can actually access this cell, and also basically set our bit line to be 0. And again, bit line bar is basically the inverse of our bit line. So it is 1. So once bit line is actually 0, we basically, if this is 0, this is VDD, and this is VDD, right? So if you look at the 3 terminals of our transistor, so it's VDD on the gate. So our NMOS transistor is on, and there's also VDD here, and this is ground or 0 here. So what it will do is basically doing a discharging operation, right? So we'll discharge this 1 or this VDD to 0 because my bit line is 0 and my gate is actually on, so that my transistor is on. So I will perform the discharging signal, and then until what I have here is actually become a 0. And when I have a strong 0, and this will basically be a 1 here naturally, right? So basically, we always basically write 0 here. If we actually want to write 0, you actually do want to overwrite the value with 0, we set it to bit line and to actually discharge this one. But if we actually want to write a 1 here to the SRAM cell, we actually, instead of write a 1 here, we actually write a 0 in the bit line bar. And again, by discharging that, so that we have a 1, by discharging that, we have actually a 0 here. So we have also a 0 here, and then it's inverted to have a 1 here. So that's basically how we do write operation by actually discharging. Again, the word line need to be specified. So word line need to be on, but actually by discharging that, we have a strong 0, so that we can, by discharging that through bit line, by lower the bit line to be 0, so that we can actually either bit line to be 0 or bit line, one of them need to be 0, right? Because we are always writing 0. We're either writing 0 to Q or we're writing 0 to Q bar. So one of the bit line need to be 0. They need to always need to be a pair. And then we can actually update our SRAM cell. So that's basically the write operation. And for, let's say for other, we always talk about their 2-dimensional array. So for other rows, if the word line is actually not specified, not selected, the access transistors are not on, right? So now I can, it's basically, I only have this cross-coupled inverter here. I don't have any access transistor. I cannot access to the external world. So nothing going on if the word line is actually not selected. So this is actually specific to the selected row so that we can actually access the values stored inside the inverter pair. So that's how we do a write operation. So let's also take a look at how we do a read operation here. So how do we do a read operation? It's the same in the sense that we still need to specify our word line here, right? So whenever we need to access something, word line need to always to be specified. So word line is always, we need to pull up the word line so that we can actually access this SRAM cell. So different from what we see earlier when we do a write operation, we always need to pull one of them to be 0, either bit line or bit line bar, so that we can actually write a 0 either to Q or Q bar. When we actually do a read, this is actually a different operation. We'll actually need to actually manage the bit line slightly differently. The word line is the same. The word line is basically always choose to whether to access a particular SRAM cell, right? So the word line is always the same. What's different is a bit line operation between read and the write. So with write, one of the bit lines, either bit line or bit line bar, need to be 0. But when we actually do read, we actually pull both bit line and bit line bar to be high. Why do we want to do that? Why do we actually want to pre-charge both bit line and bit line bar to be actually VDD? So what's happening with a read is that we want to sense what's the value actually being stored in my SRAM. I don't actually want to overwrite, right? I don't really know what's the value here. For a write, actually, I know exactly what I'm going to write, right? So yeah, I want to write and 0, I set my bit line to be n 0. If I want to write a 1, I set my bit line bar to be n 0. So I always know what I want to write. But for read, actually, I don't know. I don't know what's there, right? I actually want to just sense, access my cross-coupled inverter a little bit so that I get a sense that what's really being stored there, right? So here is actually, I want to access the transistors, not with the intention of actually overwriting the transistors, overwriting the values there, but with the intention to actually tell what's really going on here. So because I don't really know what's there, my strategy is actually, I just pre-charge both to be 1. So both bit line and bit line bar is 1. But based on the value, my SRAM cell is actually stored, one of the lines actually will start discharging, right? If I charge, in this example, both my bit line and bit line bar to be a 1. I don't know what's there, what's inside in my SRAM cell, right? And now my access transistors are also on, so everything is on. So now with my access transistor on and everything's on, I can actually start measuring how my bit line and bit line bar is actually changing. Let's say in this case, my gate, if you look at the one on the left first, my gate voltage is VDD. Drain to source, my source voltage is 1, my drain voltage is also 1, so there is nothing going on. So this is always 1. There's no charging and discharging going on here. But if we look at this access transistor here, my gate voltage is VDD, and let's see, drain to source. Well, drain to source, right? So my source voltage is 0, and my drain voltage is actually VDD is 1, right? So in this case, what's happening? Because I have 0 and 1, I actually have the voltage difference here. I have it's greater than threshold, so my transistor is on, and I have 1, I have a 0 here. So I start actually discharging my capacitors, my load capacitors here, to gradually actually pull my 1 in my bit line bar to be n 0, because I have a 0 here is being stored internally. Right, so now I start actually this discharging operation. If I'm actually, we'll talk about the peripheral circuit later, but if I'm actually comparing my bit line circuit and bit line bar circuit, in this case, I notice that my bit line bar is actually start discharging. That basically means the node actually connected to my bit line bar is actually storing n 0. And if this node is 0, the Q bar node is 0, the Q node is actually 1. So with that, we basically actually know what's actually being stored here. It's actually a 1 here. So by doing this is basically by pre-charging the circuit and also discharging basically the load here. By getting this load discharged to 0, it will not actually disturb what's already going on inside our circuit, very important. We'll actually get to DRAM later. When we actually access DRAM, no matter whether we are doing read and write, we are actually destroying the circuit, the signal, the data actually stored there. So we always need to refresh. But with SRAM, it's actually not destroying the signal, the data here. We are really just sensing the signal so that we know what's actually being stored here. So this is how we actually do the read operation here. So we're a little bit over time, so we'll not get to the later part of the discussion here, but you may notice we started talking about charging and discharging, right? Transistor is being charging and discharging here, and there are multiple transistors going on. So there's also a very important consideration for stability, so that when we actually discharging or charging, we're not actually changing the value of our SRAM cell. We'll continue this discussion next week and see how we can actually using the knowledge that we learned in our CMOS module to actually navigate how to actually manage the different SRAM, different transistors in our SRAM. So great to see you all here. Don't forget, we have a guest lecture on verification this in 2 days, this Thursday. And good to see you all. Take care, and I'll see you next week.